Okay, so last time we discussed, the majority of the time we spent discussing the idea of hypothesis testing. And we viewed some sort of alternative approaches. So the general idea was that if you're trying to do a hypothesis test, you'd form a test, which is like a binary estimator. And that test sort of produces, let's say, 1 or 0, depending on the value of y. And so there's a critical region or a rejection region where y, where if y isn't there, then you would, let's say, accept the alternative or reject the null, and otherwise you stay with the null. And we saw that usually that in the test that we work with, there is some sort of a test statistic, which sort of reduces y to something else, like a t statistic. So in the context of regression, for example, when you're trying to do a test of the coefficient being 0 or not, what you would do is you would form this t statistic based on y, which is indirectly based on y. It's based on beta hat and the estimate of the variance. And the way that these tests are usually set up is that you compare this statistic with the threshold, or the absolute value threshold, and so that would be the test. So the test would look like something like that. And then you want to control the type 1 error probability, also called the size of the test or the significance level. And this is equivalent to computing this probability that this is the probability of rejection, basically the probability that this is 1. And you set it equal to alpha. And we saw that, let's say, if this is the t statistic, this is equivalent to rejecting based on the interval, the confidence interval that we built, not including 0. So you either sort of drive this threshold on the t statistic under the null, which is the threshold would be dependent on the quantiles of the t distribution, or equivalently, you can state the test as 0 not being in the confidence interval. An alternative characterization is via the p-value, which we discussed last. And so we discussed a little bit about the idea that the p-value, a proper way of viewing it is as a transformation of a random variable, but the transformation that puts it in the scale of probability. So it's sort of not a probability, but looks like a probability because it's of the type of probability. And the idea was that you'd form this transformation of based on the distribution or the complement of the CDF, basically, of the absolute value of t, and you apply it to the statistic. And when you apply this, that's how you compute basically the p-value. This guy is going to be as a random variable, uniformly distributed under the null. And so in particular, if you reject, when this is less than alpha, the probability under the null would be just alpha, because that's how a uniform distribution behaves. If you have a uniform random variable 0, 1, the probability that's less than alpha in 0, 1 is alpha. And so the advantage is that first, every test is sort of like a normalized, or there's a uniform approach. So if you give me the p-value, and if I compare it to alpha and reject when p-value is less than alpha, the test that I get is going to automatically have a significance level alpha, type 1 error alpha. The other reason is that because you can report this, and how far this is below the threshold is also informative. It sort of tells you that gives you some confidence, or like level of surprise. They call it different things. So it's not a probability, but it gives you like some idea of how far away from null you might be. Because you'd expect that under the alternative, this is not uniform. And it is usually that, so under the null, P, let's say Y is uniform under the null. So if you plot the CDF, it would look like this. However, under the alternative, usually you'd have something which is like concentrated near zero. So it's like most of the time, hopefully, it's like very close to zero. And the more concentrated this gets, so it could be something like this, or it could be something like that, or even like this. So the more concentrated towards zero, the higher the power of the test. So basically, when you reject at level alpha, the probability type 1 error is the area here, and the power is basically would be the area here under this curve. And the more concentrated towards zero it is, the higher the power. So, okay, so that was the idea last time. Any questions for the ideas that we discussed last time? Comments? So p-value is clear to everyone, hopefully after this course. So the idea is, again, it's a frequentist idea. So any single p-value that you compute in practice is not necessarily meaningful. But if you repeat the experiment many times, under the alternative, you'd observe things that are much closer to zero on average, whereas under the null, you'd observe something which is uniform. Okay, so we covered this, and I also discussed this example. That's basically the duality between the confidence interval and the hypothesis testing, and also how to compute the p-values. I believe you know these things, so I'm going to skip that and also discuss this. So up to this point, we have discussed all the material. Now, did you guys get a chance to go over the rest? So has anyone looked at this slide and the lecture corresponding to this? Anyone? Okay, no one? Interesting, okay. So I'll let you look at it in the lecture videos. I'm going to briefly mention. So what we so far worked out was, let's say, so far CI for, let's say, beta I, a single coefficient, or hypothesis testing for beta I. But we could generalize this to basically can generalize to A transpose beta for any linear combination. So, or any vector A. So AI, beta I, or J from 0 to P. So if you look at A transpose beta, that's a different parameter. It's a new parameter. So let me maybe do it. So far we have CI, or hypothesis testing for a single parameter. But say for example, what if you want to have a CI for, let's say, a linear combination, beta 1 minus beta 2. Okay, so beta here is beta 0, beta 1, beta 2 up to beta p. So the idea is that I can write beta 1 minus beta 2 as A transpose beta for some vector A, right? So what would that vector be?
It would be 0, 1, -1, and then the rest would be 0.
Okay, great. Yeah, so that would be that. And so if I want to build confidence intervals for a parameter like this or do a hypothesis test, so you can imagine, so for example, I could do a hypothesis test that beta 1 minus beta 2 is 0 versus beta 1 minus beta 2 non-zero. So that would be equivalent to testing beta 1 is equal to beta 2 or not. So we can test whether the two coefficients are equal. So in order to do that, I have to build confidence intervals test statistic based on this. So what is a natural estimate of this quantity? So if I want to estimate A transpose beta, what would be a natural estimate? So we have an estimate of the entire vector. You have a beta hat, right? Estimator, the OLS, ordinary least squared beta hat for beta. So how do I estimate that quantity? Anyone? Should I call on people? Let me try. I'm gonna randomly pick. There are 7. Random number. Okay, Albert, do you wanna comment? Let's see.
I'm not sure.
Okay, so 1, 2, 3, 4. Phase, do you wanna comment? How do you estimate? Let's say, for example, you have. Right, go ahead.
I'm honestly not too sure as well.
Okay. Another number 1, 2, 3, 4, 5. Karan, how do we estimate? So let's say I want to estimate this quantity, beta 1 minus beta 2. What is a natural estimate? The random number sort of repeats. So let's see, Karan, Sehong.
I think regression function, the mu of x beta at the vector, the
X beta. So we'll get to the regression function, but let's say I just have someone ask you, so you don't know beta, okay? Someone asks you, what is your estimate of beta 1 minus beta 2? And you have access to the entire vector beta hat. So what is the natural estimate of beta 1 minus beta? It's very simple.
Is it just A transpose times B hat? Beta
Okay,
hat?
great. Yes. So it's just X transpose times beta hat. So you just replace this with beta hat. So let's say if I ask you what is the estimate of this, so you have an estimate of this and you have an estimate of this, you just form the difference. Right? That's the natural estimate. So it would be equivalent to saying A transpose times beta hat, which just in this case would be beta 1 hat minus beta 2 hat. So this is called a plugin estimator. So plugin, a plugin estimator for A transpose beta. So if I want to build a confidence interval for this, I have to determine the sampling estimate. This is my estimator. I have to find the expectation, the covariance matrix, the whole distribution, and try to find a pivot based on it and proceed. So what is the distribution? So let's say I know I'm under the E2 under the Gaussian assumption. Gaussian assumption and the noise. What can we say about the distribution A transpose beta hat? So I know that beta hat has this distribution normal between beta invariance, covariance sigma squared X transpose X inverse. So what would be the distribution A transpose beta hat?
Is it just sorry, go ahead. Please go ahead.
Oh no, you can go.
I mean the mean, is it A transpose times beta?
Why?
Because the expectation of A transpose beta hat beta is actually AE transpose times expectation of beta hat.
Right. What is this property called? Okay, this there is a chat. Unbiased. No, this property. We get to the unbiasedness. Why can I take expectation inside? Something of expectation. What is that something? Linearity. Okay, Hortensia. Good. Linearity expectation. So this is also, we have computed that this is unbiased for beta. So this is beta. And so we get A transpose beta. So we conclude that this, in fact, is unbiased for this. So we're trying to estimate this, and the expectation of our estimate is equal to that. So A transpose beta hat is unbiased for estimating A transpose beta. Good. So how about the covariance matrix?
Is it
covariance X transpose beta hat?
Can you say that again?
Covariance X transpose.
Covariance? You mean
A
covariance of what?
So A transpose covariance beta hat A.
Okay, yes, that's the formula. And so this is sigma squared X transpose X inverse. So what we get is this whole thing would be, just A transpose sigma squared X transpose X inverse A. Okay. So what is this? What is the whole distribution?
Is it normal?
Why?
Because it's affine transformation.
Okay, good. Affine transformation of beta hat. And beta hat has a multivariate normal distribution, so this is going to have the same.
Right?
Yeah, multivariate normal, yes. This is, in fact, one-dimensional, so it's just usual normal, which is a special case of MVN. Right? A transpose beta hat is just a number. But nevertheless, it's an affine transformation of a multivariate normally distributed vector, so it has to have multivariate normal distribution. So we have calculated this, and if you go back to your the way that we drive the T statistic, so you subtract this from that, and then, so this is replacing like beta I. This was beta hat I. This is replacing beta I, and this is just sigma squared times some like v squared or we had like VI or something like that, maybe V. And so everything else goes true. So instead of, this used to be for the beta I, this was the ith entry, but that was a special case actually. So that's a special case where the A just has a single entry 1 and the rest are 0 at location I. Now instead of that quantity, like the diagonal entry, you just have this other scalar. And so if you go back to the proof that we did for the TSS, everything goes true. So in the end, what you end up showing is that A transpose beta hat minus A transpose beta divided by the standard error of A transpose beta hat. This is T n minus D. D is P plus 1. And the standard error of this, so what is the standard error of this guy? How do you compute the standard error of this?
S times square root 0, 1, -1.
And for the general A?
The 0, 1, is it right? -1.
So this is a special case. So what if I have a general A? Can you just state a formula for the general A? What is the procedure to obtain the standard error? What is the standard error? Or what does it mean?
Is it a whole thing in the normal distribution?
The whole thing. So what do you mean?
Like A transpose covariance beta times A over sigma square times X transpose X inverse?
Can you say that again? So you're saying, okay, let me just, so I'm gonna open it. So we're asking what is the, we're trying to figure out what is the standard error of A transpose beta. So tell me again, what is it?
Like A transpose covariance beta hat times A
Okay.
over sigma squared times
Covariance sigma squared
over sigma squared
over sigma squared.
Times X transpose X inverse over yeah.
So how did you come up with this?
Oh wait, sorry, isn't that just A transpose covariance beta hat A without the sigma square and the inverse of X transpose X?
So then why is this?
That's the variance of A transpose beta hat.
Okay, good. So that's the variance. We have figured this out. That's actually, there's a sigma squared there as well. So the variance of this is sigma squared A transpose covariance of beta hat A. This is the covariance matrix, which is just the variance because things are univariate. So we have calculated this already. So style, right? So that's the variance. In fact, this is the variance of A transpose beta. Because it's a univariate object, the covariance matrix and the variance are the same. So we have this is correct. So now what is the standard error? What is the relation of the standard error to variance? Divide by square root n. So so the idea is this is sigma squared A transpose covariance of beta hat A divided by square root n. So that potential is saying that, is this correct?
It's an estimate for the standard deviation.
Okay, great. So you already have to go back to, always go back to, when you have a question, try to understand what is the definition of the quantity, let's say. So standard error, A transpose beta hat is, can you say that again?
An estimate for the standard deviation.
Estimate for the standard deviation of A transpose beta hat. Okay, that's a standard deviation of A transpose beta hat. So what is the standard deviation of A transpose beta hat?
It's the square root of the variance of A transpose B.
Okay, that's by definition the square root of the variance, which is, this is the variance. So the square root would be sigma A transpose covariance of beta hat A, right? No, root here. Okay. That's actually not correct. So this was not correct. This is A transpose covariance of beta hat A. So there's no sigma squared. Sigma squared is in the covariance of beta hat. So this would be sigma squared A transpose X inverse A. Now everything is known except sigma. So this would be just the square root of this object, which is sigma A transpose X inverse A. Okay, so now what is the standard error? What is one way to drive this? The standard error is an estimate. You can have different estimates. But what is the common estimate that we use? It's not a unique thing, so you could have different estimates of
Standard deviation over square root of n.
standard deviation over square root n. Is this correct? This is really informative to me.
minus 1.
Where is n minus p minus 1?
N minus d.
Oh, okay. So this is another like standard deviation A transpose beta hat divided by n minus p minus 1 under square root here. So this is the purpose of this course, to try to avoid doing these guessings. These are not correct. So going back to the definition, this is an estimate for the standard deviation. So we first calculate the standard deviation. We know how to do it. That's the standard deviation. Now, what is wrong with this? I don't know sigma, right? I know A, I know X transpose X inverse. So this part is known. This is unknown. So what is the natural estimate of this quantity? If I want to.
You use S instead.
Okay, good. So this is not, this is not, this is not. You just replace the unknown with your estimate. This is again a plug-in estimate. Just replace this with S. So you get root A transpose X inverse A. Okay, so you don't have to like guess. It's just you compute, and then what is the natural thing? This is like a plug-in estimate. You don't know sigma here, I just plug in S there. Right? S is my estimate of sigma. If you have a different estimate, you get a different standard error. But in this course, we use S usually, so that's R. So now this is an estimate of the standard deviation. It's and the standard deviation is obtained by computing the variance, right? So this was very good. You don't need to divide by root n. There's no need to do that. In fact, if you do divide it by root n, that would be wrong. So Is that okay?
Could you say how to calculate S again?
Okay, someone tell me how to calculate S. How do we calculate S, which is the, I guess, we calculate S squared and take the square root. So S squared is the estimate of sigma squared. So what is our estimate of sigma squared? That's the same thing as before. So once you fit the regression, there's one estimate of the noise variance. It's the same estimate that we used before. That's not going to change. So
Y transpose Y minus beta hat transpose X transpose Y. I mean, SS reg divided
sorry?
by.
So what?
Yeah.
So can you I mean, tell me what I need to do to complete this, like Y transpose Y minus beta hat transpose
X transpose Y.
Y. Okay. That's it?
Yeah, I think so.
So how do you come up with this? This is interesting, but I never mentioned this in the lectures. It's related to this, but what is like the easiest way to say it? Not the
Is
most.
it like E squared over divided by n minus p plus 1?
E squared norm divided by n minus p plus 1. Yes, that's the right way. So the error.
Oh, sorry.
Okay.
I was just gonna ask, how do you like calculate or like find the E in this case?
How do you define before? There's no difference. So there's just one residual. You're not refitting the regression. There is just one. So you have the regression problem, right? Fit the regression. You get beta hat, which is X transpose X. This is the OLS estimate. And then everything else follows from this. So mu hat is X beta hat, E is Y minus X beta hat, and so on. Right?
Professor?
Yes.
Can you just divide by the degree of freedom? The denominator is just degree of freedom, and the numerator is SS reg.
Which expression are you talking about?
That's why I got the Y transpose Y minus beta hat transpose X transpose Y. Yeah.
Divided by?
I mean, this means SS reg divided by n minus.
SS reg? What do you mean SS reg?
The residual sum square.
SS, you mean SSR?
Yeah, SSR.
Divided by?
N minus T minus
1. So we'll get to that. This is called SSE. So if you're trying to estimate the variance, this is the sum of squares of the errors, or residual sum of the squares. You don't divide SSR by n minus p plus 1. But what you have here is correct. This is not the top is not the SSR. So this part is the SSR. This would be the SST, like close to SST, but not exactly the SST. But you should be able to drive anything. So whether this is correct or not, you should be able to do it. E is this, so that's the formula that we had. And we had some sort of an argument for this. It's just that didn't come out of the thin air. So we did the maximum likelihood estimator, and the maximum likelihood estimator turned out to be, actually like sigma hat squared, which was this guy. This turns out to be the solution of the NLE. But I mentioned that for some reason we replace n with this because this makes this unbiased, and we'll see it again later on. You could have easily used the MLE here. You could have used sigma hat. This gives you like another different estimate of the standard error. It's going to be close to the previous one if n is much larger than p plus 1. When n is close to p plus 1, then this might be more accurate. S squared. So I'll come back to this expression, but let's say, Diana, does this sound good? Did this answer your question?
Yeah, it did. Thank you.
Yeah, so you're not doing anything with the fitting procedure. Everything is the same. We're just trying to figure out what the distribution of this is. And then once we have the distribution, we have the standard deviation. And once we have the standard deviation, we can find an estimate of it. So the right way is to try to find out what the standard deviation is of whatever quantity you're trying to build confidence intervals for. In fact, you have to do like the entire distribution. But let's say in our course, most of the things have, most of it, not all, have normal distribution. So you figure out the standard deviation, and then you open estimate. Okay, so a couple of things. So going back to this, so this is mu hat times y. That's mu hat, right? And so what this is saying is, what you're effectively claiming is, claim norm e squared is y squared minus mu hat times y. Okay. If that's the case, then your formula, I guess it was Albert, right? So your formula would be correct, right? So far, so good.
Mm.
Is it clear that this is equal to y hat times y?
Yes.
Yes. Okay. So do you remember the orthogonal decomposition that we had for y? Anyone remembers all the things about orthogonal decomposition? So what was the orthogonal decomposition? The projection idea, there was the composition of y into two pieces that were orthogonal to each other. Anyone can contribute.
The error plus the explained part.
What is explained part?
Is it beta x?
Beta x. Can we have a better guess? Beta x. I can't multiply beta by x because this is like 1 by p plus 1.
Beta transpose x transpose beta.
X transpose beta is as bad because the dimensions don't match. By the way, beta is unknown, so that wouldn't be necessarily the best decomposition. So we have a decomposition for y. Both of its components we know, they're orthogonal. And that's exactly what the regression is trying to do, if you remember. So let's go back way up. It's not here. Okay. So let's go back to here. So this is the geometric picture that you have to remember. Where is the geometric picture? So that's the picture. So when we do regression, we project y onto the image of x, and so we get a orthogonal decomposition. So what are the pieces here?
U and E.
U? We don't have U here.
U hat.
Mu hat. Okay, so mu hat. This is mu hat. And E is
The other E.
Epsilon. So if I add this,
Oh no,
to
sorry,
this guy,
sorry, the little E.
the other E, okay. So if I add this to this, I get back this. And this is orthogonal to this. So, and it also helps to remember that the residual is just y minus mu hat, okay? It's just not that difficult to remember. But the key is that this piece is orthogonal to the other piece. You can see E is orthogonal to mu hat. The reason is that E is orthogonal to the entire image and mu hat is in the image. Okay, so this is what you have to remember what the regression is doing geometrically is that. Okay, so now if you have that, mu hat plus E, mu hat is orthogonal to E. Why? You have to ask yourself, but hopefully you know. Now I have E squared. I want to establish that inequality. So I write it as E inner product with E. Okay, or if you want, it's just E transpose E. And I replace one of them with mu hat. So like y minus mu hat. This is E. I'll keep the other one. Right. So what do I conclude? Y transpose E minus mu hat transpose E. Can I simplify?
Mu hat transpose E is 0
Why?
because they're orthogonal to each other.
Okay, because they're orthogonal. So this is going to be Y transpose E. So that's one formula. Now, what is Y transpose E? Y transpose E, I'm going to repeat this. Y minus mu hat.
Yes.
Okay. Questions? So how about root n? So where this root n comes from? So again, if you understand what you're doing, you don't have to guess. You can write this as A transpose beta hat is equal to S root A transpose X inverse A. I can divide this by root n, and I can put X transpose X over N inverse A. Why can I do this?
The ends just like cancel out.
Good. Yeah, so this n comes out, goes to the numerator and cancels out with this. Okay. So you don't have to do this, but I just wanted to let you know, no need to do this. To do this. But because you mentioned root n, so you can write this. It's often nice to write this like that because this is going to have, this is like the Gram matrix divided by n. This is going to stabilize because you're multiplying as you get more and more samples. Remember, x is n by p plus 1. If you do this normalization, as you get more and more samples, this gets big because you get like you end up. This is like X transpose would be like this. This would be sorry. This is X. This is X. This is X transpose would be like that. P plus 1. This would be X transpose. This would be X. When you multiply out, you can see each row when you go to compute each row. You're basically multiplying something that has n elements by something that has n elements. And as the sample size grows, this is going to grow like n. So this gets big. If I divide by n, this stabilizes. Eventually, we can argue if things are random, x transpose x over n is roughly, let's say, it's like a covariance matrix. Approaches the covariance if things are normal. I'll try to maybe, I don't know if I do. We don't think of the x as random, but if you think the rows here are random draws from, let's say, a distribution independently, then this would, and things are zero mean, then this would be a covariance matrix or a second moment matrix. So this stabilizes, and this whole thing stabilizes as n goes to like infinity. This is not going to blow up, and this is going to converge to something constant. And this part, you can see it is going down like s over root n. So the standard error gets smaller and shrinks. So this is like the base that every estimate in your like regression problem just shrinks down by this much, and then this extra factor is different for different quantities. So if you're estimating beta hat, that would be different. Like if you're estimating beta 1 versus beta 1 minus beta 2, that a would change here, but that's sort of the specific adjustment that you make to this global standard error. So if you understand all of this, you don't have to think like, guess, this is correct, and there is a reason why you do this, because this is like the parameter grade, things go down like this, but you don't have to do it. I mean, this is a perfectly fine object, and you can work with this. Sometimes in the exams, I might give you this guy instead, and so this version might be easier to work with, and so on. Sounds good? No problem. So, Hortensia, glad it was clear. Right. Any other concerns or questions? Okay, so if you look at the slide, everything that I did here was I can replace this instead of working with A transpose beta hat, let's work with X transpose beta hat, where this X is just another name for A, let's say. It's just a renaming of this vector A, but this is oftentimes referred to as the regression function. The reason is that, I mean, I changed the notations because if you think of what the regression is like xi transpose beta plus epsilon I. If I write each observation would look like this, where this is the so xi transpose here is a new, sorry, is a row of the data matrix. Okay, so this is xi. So if I look at the ith row of X, that would be xi transpose. And then I have an observation here. So this is the y vector. And so this would be yi. Vector, this is vector y, and so this is yi. And so for every row, you have the covariates, and then you have the observations. And you can say that yi is, in fact, equal to mu of xi plus epsilon, where this function for any x, this is like a dummy variable, is defined as x transpose beta. Or if you want, it's like beta transpose x. And if you remember, this is a linear function. So this is a linear function of x. It's like an affine function, but with 0 coordinate. That's why this is called a linear regression, because you're modeling the mean. So this turns out to be the mean of y, because this is 0 mean. And so you're modeling the mean of y as a linear function. And a general linear function can be written, of a vector can be written as beta transpose x. Okay. If I change the definition of this function to something nonlinear, that would be probably called nonlinear regression or non-parametric regression. But in this class, we call it. The reason why it's called linear regression is sometimes because it's also linear in these coefficients, but that's fine. This function is, if you view it as a function of beta, it's also linear in beta. But mostly because this function is linear, okay, as a function of x. So the relation between y and x are linear. So the advantage is that now I can ask for confidence intervals for this whole function. So if you give me x, a new x that I haven't observed, I can evaluate this. If I have an estimate, so an estimate of the regression function, this would be a plug-in estimate. I just plug in beta hat. So everything we have done, just replace a with x, and this would be exactly the same. So it's just everything that we did was actually doing the same things, but mathematically the same. It's just the name of a, we just renamed it to something else to be more informative. So this is now a plug-in estimate of the regression function. And so I can evaluate what would be the expected, this guy at new x's. So I could have like a new x coming in here that I haven't observed. This is a new x. So I don't know why. Okay, so that's my guess for the mean of y. And so I can try to build confidence interval for this, which would include the mean of y, mu of x. So this would be mu of x plus noise. I don't get to observe it, but I can try to predict it. So that leads to the idea of estimating the mean of a new observation, or predicting the value of a new observation. So we can build confidence intervals for this. We can do hypothesis testing for this, all of that. So everything sort of is the same as what we had done before. So mu hat x would have mu of x. This is like x transpose beta. This is x transpose beta hat. It's just like what we had, a transpose beta hat, a transpose beta, and this is like exactly the same, a transpose. Remember, it's like I have it here. So replace a with x, everything goes. So it's just like a transpose beta. And so this is the mean, this is the variance, the square root is the standard deviation. Replace sigma with s, you get this. So that's the standard error of mu hat. And so a confidence interval for mu of x turns out to be like mu hat plus minus gamma times the standard error of mu hat x. And that gamma is just the same quantiles of the t-distribution. So everything goes as before. So mu hat x minus mu x divided by the standard error of mu hat x. This is t n minus d degrees of freedom, and so on. So for example, you can build confidence intervals for this guy, or you could build confidence intervals for the mean of a new observation. These are all the same mathematically. So I give you the new observation, so all the covariates for a new observation, and ask you to compute a confidence interval for the mean function or the regression function, evaluate it at that point, and that gives you this gives you all the tools that you need. And so in the usual regression, like the simple linear regression, what you end up having is like the x would be just this would be like 1 and a single entry, right? That's the first is like the intercept. The second, there's just one covariate, and that one covariate would be just this x here. This is like the, if you want, it's called x1. Let's say this x is 1 and x1. Simple linear regression, and this would be y, and so this, the line is going to be mu let's say of x1. This is just going to be beta 0 plus beta 1 x1, which is just nothing but beta transpose x. And you can say it's a line, and you can build confidence intervals at every point. So given every point, given any x1, you'd have a confidence for this value. And you can see that the confidence, there's a square root, this like, it's going to change. So as it's not going to, the length is going to change for different x's, okay? Depending on how things go usually. So the center, the more you move away from the center, things would change. So there's going to be some sort of a, if you draw the back, like the envelope of these intervals, it would be something like that. So that's this function. So if you plot this as a function of x1, that's the twice this is the length. So the center is this. So actually, it's not going to be. Sorry, this is the. Yeah. So there's a true regression line. I forgot which one is. Fine. I forgot how I plot this. So there's a true. Let's say this is the true one, and there's an estimated one. The estimated one could be like this. I don't know. Okay, and then your confidence interval would be intervals around. So this is going to be mu hat x. Okay, this is the estimated regression line, and then the confidence interval at each point would give you an interval around this, and so it might be something like that. And so you'd have some sort of a envelope, and this envelope sort of the true line, which is this guy with 95% probability, like probability 95% would be in this envelope. And so if you repeat this experiment, 95% of the time, the entire regression line would be within this. So not all the time, but every time you repeat the experiment, you'd have one of these envelopes. And 95% of the time, this envelope contains the regression line. So you get, that's the meaning of the sort of the confidence intervals for the regression function. And then there is a prediction interval, which is trying to estimate this new value, like try to build a confidence interval for this new value, not just the mean, but the entire thing. And then there's this extra noise there that you have to account for. And I'm not going over this, but this is discussed in some lecture videos, or you could ask your TAs if you have questions. There's this extra noise here. In addition to this, I have to account for that when I build a confidence interval. The effect is that there's an additional +1 here under this square root. So if you do the calculations, this guy minus the new noise would have the same properties with extended some variance here. And then when you compute the standard error, because of this, you'd add a +1 here. So this is discussed a little bit in more details in some of the, hopefully some of the lecture videos. But the idea is the same. So you'd have some estimate or a pivot, and then based on that, you build a confidence interval. Okay, questions, comments?
So the prediction part, the epsilon, new epsilon.
Yeah. What is about the new epsilon?
Is this also normal distribution?
Yes, this is still from our model, so this is going to be normally distributed. So what happens is that I want to build a confidence interval for this, right? And the way I'm going to do it is that I have an estimate for this part. This is going to be mu hat x mu my. And then if I look at mu hat minus epsilon mu, these are independent. So this is based on epsilon 1, epsilon 2, up to epsilon. And these are the noises that I had in the sample, the training. Sometimes in machine learning is called the training. This is a new observation. This is like a test. this is like a test point. So this
So they
they're
are
inde-
independent.
yeah, they're independent because this new noise has not been included in the estimation, and we're assuming that whenever new observations comes, the noise is independent of all other observations. So they're independent. Because they're independent, you can argue that mu hat basically x mu, this is multivariate normal. Okay, and so this is an affine transformation of that. So this whole thing is going to be normal again. Okay, by independence, this part is normal, this part is normal, and the two pieces are independent. This whole thing is going to be normal because it's linear transformation of that. And the variance, if you know, what is the variance of a sum of two random variables if they're independent?
The variance
is
x. Oh yeah.
Variance x plus variance of y. In general, there is another term which is 0 in this case, okay, because of the independence. So you get the variance of this, which is this, plus the variance of this, which is sigma squared. And the mean of this is 0. The mean is just going to be that. So this whole distribution comes out like that. Now, if I have this, then you can easily see that if I subtract, I have this. If I subtract mu, I get a normal. So I get mu hat x nu minus epsilon nu minus mu of x nu. I'm subtracting the mean here. So this would be normal, which means 0, the same variance. And then if I divide by standard error, because this is 0 mean, if I divide by the standard error, I get a t-distribution. So this has a t-distribution. And so you can see this is negative mu nu. And so this allows me to construct a confidence interval. So this is the center of the confidence interval for y mean, y nu. And so what I would get is y nu is within an interval this plus minus that with probably 95%. So there's a bit of argumentation going there that you have to understand. These two pieces are independent. If I add two independent Gaussian variables, they're going to be, the result is Gaussian because we're effectively working with a linear transformation of a multivariate normal distribution because of the independence components. When I stack them, they're multivariate normal. So this thing is an affine transformation of this. So it would be multivariate normal. And then I just have to compute the mean and the variance. The mean is like simple. The variance is just the sum of the variances because they're independent. So you get this plus that. And if you center this, you'd get, once you center, you get this y nu here, which is what you want. And you see that this minus this divided by that is tn minus t plus 1. So this is saying y nu belongs to this. The probability that this belongs to this is 1 minus alpha. That's how you build a confidence interval for this. Okay.
Can I say the denominator part is just standard error?
Yes, this is just yeah, it's a little bit tricky because
But I'm not sure. But
you can say this is the standard error of this, but you okay, so it's not fine. Yeah, you could say this is the standard error of what? Standard error of this guy, but this is not an estimator. Usually when you talk about standard error, you're talking about the estimated standard deviation of an estimator, and this is not an estimator because I don't know epsilon. But it's fine if you want to say a standard error. It's just the estimated standard deviation of this quantity. That's fine. If you extend the definition of standard error, just the an estimate of standard deviation of anything that you care. Yes, then this is the standard error.
So the denominator part,
yeah, you can say this is this.
Yeah, okay.
Yes, this is the standard error of mu hat x nu minus epsilon nu, if you want. They don't usually call it that because this is not an estimator, but the concept is the same. So this whole thing. you can say it's just if you take the square root of this and replace it with s, that would be just an estimate of the standard deviation of this. That's exactly what it is. Right?
Okay, thank you.
Yeah, it doesn't matter what you call it. You just have to understand why you're doing these things. The reason why we do this, like everything goes like this part is again independent because of the independence of s and beta hat. You remember this whole part, the above is independent of below, and because this is independent of everything else, independent of this, and this is also independent of this, and they could be dependent because they're based on the same data, but they're independent. You established that because this is dependent on. This only depends on beta hat. If you go back to nu hat, x nu is just beta hat x nu transpose. And so beta hat is independent of, this is also dependent on just E. And so the independence goes there as well. And so that's why this becomes a t distribution. It's exactly the same as before. You use the fact that this is, if I divide this by the standard error, by the standard deviation, after centering, the result would be normal. But then when I replace sigma squared with s squared, I get the t distribution because of the whole independence business. So that's exactly this argument. If you want, you can go through the exact same argument that we did here. So you write this as this times that here is just, this guy is complicated. And this guy is just something else. This is something else, but the exact argument goes through. So things have the same distribution as what we had before. Okay.
Yes.
Okay. Any other questions? Good. So we actually talked about the prediction interval as well. So you can see the reason why this is there is because I have to include this noise, and there's this extra factor of 1 that I pay. So prediction interval is larger a little bit because you have to account for the fact that you're not just estimating this line, but something which is randomly distributed along this line. So it's going to have, like, you have to take a bigger interval to contain it. Okay, so this like chapter of the course is done. We're still in chapter 4, but we're now going to move on to testing something a little bit more general. So based on the previous discussion, you should be able to test beta 1 equal beta 2 versus beta 1 not equal to beta 2. So if you understand what we did today, you can build hypothesis test. So all the things that I discussed about confidence intervals just carry over to the hypothesis test. So if you understand the duality, it's just equivalent to do the test at level alpha. You can just build a confidence interval at level alpha and see whether 0 belongs to that interval. And this is equivalent to testing whether this is 0. And this is just equivalent to testing A transpose beta is equal to 0. And so if you have a confidence interval for this, then you're done. Or you could just form this A transpose beta hat divided by standard error of A transpose beta hat. Under the null, this is 0. This is going to be Tn minus D. And then you can set the threshold. So the probability that A transpose beta hat this is bigger than T and minus 1 minus alpha over 2. This is going to be alpha. And so if I have a mistake. So the test is this. So you're going to reject if this is bigger than the threshold or not otherwise. So it's very similar to testing for beta hat I. It's just the only thing that's different is the standard error. And of course the variance. So the estimate and the standard error. So the way that you form the t statistic is a little bit different, but everything else is similar. Okay, so we can do these tests, but how about I want to do, for example, beta 1 is equal to beta 2 and beta 3 is equal to beta 4. H1 is otherwise. Okay, so how do we do a test like this? Assuming that we can do a test like that, if my hypothesis contains two of these statements or two of these statements, how would I do it? Anyone has seen this before? This is an example of a multiple test, sometimes called multiple hypothesis testing. So if I have two hypotheses at the same time as my null, it's actually a single hypothesis that contains two pieces. And I know how to test each individual one. How do I test them jointly? Is there a procedure for doing this? Has anyone seen like multiple hypothesis testing before? Yes, no? I suppose not. So there is an approach which you can use these t-tests. So these are going to be t-tests. You can use the t-tests. You can separately test this, and you can separately test this guy, and then you can adjust the significance level such that as you can reject, for example, you're gonna reject this null hypothesis if either this or this fails to be true, right? So you want this and that to be true under the null, and if one of them is violated, you should reject. So you could separately test each one, and then reject if either of them is rejected. But then the significance level of the test might not be correct because we developed it only for this single hypothesis test. There is a simple naive correction which you can do. You can test at a level which is, let's say, half alpha, so alpha over 2. If you test at level alpha over 2, you can show using the union bound that the test that you get out of these individual ones will have a size which is at most alpha. The type 1 error probability is controlled. I discussed this in detail in one of the lecture videos in spring. This is spring, so winter 2021, the last quarter. So if you could look at the lecture video that starts talking about general linear hypothesis testing, I go over the great detail because someone asked that, and we go over a great detail of how to do the naive approach. What we do in this course, though, we're going to develop a new test to specifically test this joint hypothesis more efficiently. And that's the idea of testing a general linear hypothesis that's there. We're out of time, but I encourage you guys to start reading this and go through these slides and the lecture videos for the next time. Next time, I hope when we come back, you guys can, so one of you or some of you can sort of start the discussion and tell me whether there was anything unclear. This might be a little bit new to people, so it's good to pre-study or look at the videos before you come to class. Okay, sounds good. Questions, comments?